chill for a minute, okay? We're gonna take a minute to just digest what just happened because I know everybody had a mini panic attack, which is fine. It's fine. We're fine. Okay. I need to join. Rosemary's gonna go watch Venom, and she's gonna have a great time. And we're going to. No, we did not just try to get rid of you guys. We love you guys. Okay. Bye, Rosemary. All right. So give me a second. I'm gonna get myself into the meeting on my iPad so I can share screen with you guys. This is probably gonna be chaotic, so just give me like 2 minutes, and we're gonna get started again. Okay. Bear with me. Daniel said he was waiting for Chris, and Rose ended the meeting. That's really funny, but no, that's not the reason. We had some errors, so just bear with me. Most savage thing I've seen in a while. Quick question: since you did SI on Monday, are you able to send out the answers to the pages that we did, or no? So I do have the recording up. Hold on, guys. Sorry, give me 1 minute because I'm like trying to copy the link because I forgot that you have to like copy the link and then post it into your browser. Okay. The recording for that is up already on my Canvas page, so you can watch it from there. Guys, I'm gonna cry. This thing isn't working. All right, we're gonna have to manually input information. I hate WebEx. Anyways, Rose and I are going to try and just, you know, kind of do it ourselves. With this sheet itself, I'm going to try and fill out the sheet itself and then post it. I'm trying to get all this stuff done at once, but of course, you know, I'm one person and I have a lot of exams coming up too, so I'm trying my best. Let's see if this lets me join. You're gonna let me join. Meeting password. I can't see your guys' chats right now, so just give me 1 minute. I'm trying to like type in the meeting password because this was just, yeah. I don't know why she went to the movies today, but okay. Okay, let's see. I'm gonna mute myself. Okay, I am back in. Give me a minute. Let me start sharing screen. I need to give myself post rules. Oh, fudge nougats. Okay, we're fine. We're fine. Change role, make presenter. Passing presenter privileges, come on. All right, I think it did it. So, share screen, start broadcast. Fingers crossed this works. I haven't done this in a while. Oh my God, sick. Cool. Okay, we are back. I am back. I'm gonna move really quick over here. Okay, so I'm gonna sit over here so then you guys don't awkwardly see people walking behind me. All right, and I'm really short, so that's why I just sunk into the chair. Okay, so here we go. So reaction energy diagrams, that's what we left off on. So if you guys have any questions, I'm gonna answer them now. But let's go ahead and just discuss this for a minute. These are two different reaction energy diagrams, okay? They're still comparing the same exact thing, all right? So in this one here, we're talking about lower activation energy and lower potential energy, all right? The product that has the lower activation energy, aka the smaller hill, is going to lead to your kinetic product. So lower activation energy equals your kinetic product. But your thermodynamic product, you're looking for which one has the lower potential energy. So since this line is lower than this line, this is going to also be your thermodynamic product. So in this situation, A is both your kinetic product and your thermodynamic product. Does that make sense? Yes? No? Okay. All right.
Wait, why is A also the kinetic product? Shouldn't the activation energy be the kinetic product?
The activation energy, you're looking at the hills of the activation energy. So this bump to go from this area to here is a smaller hill than going from here to here. You're looking at the height of this hill at this line. So since it has the lower hill, it has the smaller hill between the two, that's why A is also going to be your kinetic product.
Right, but on the last example, Rosemary put the kinetic product as being that like transition state on top of the hill.
It's not the transition state, it's the end product. It's kind so do I have it on here? No, I do not. Okay, let me see. So this is like the hill. This is the top of the hill here that leads to the kinetic product here. Does that make sense? Like these are the hills. These two forms are the hills. So it'll either lead to this one or this one. So the
Right,
carbocation, yeah.
but like in the last one, the one that Rosemary just went over, why did she put like the arrow like for the kinetic product on top of the hill?
She was just showing that that hill, because it had the lower activation energy, that's the direction that we're heading in for the kinetic product. So
So in
like
actuality, in the last example, both the kinetic and thermodynamic product would have been A as well, right?
yes, because you're looking at which one has the smaller hill to distinguish the kinetic product, and then you're looking at the lower line for the thermodynamic product. So when I go over this one, you'll see the difference between the two. Okay, so I'm going to attempt and do this one really quick. All right, so this is a different looking hill than the one that we had above. So once again, compare activation energies first, or potential energies, it's really up to you. But remember, activation energy, that hill is for the kinetic. The actual lines itself right here are your thermodynamics. So which hill smaller, is it going to be this one on the left or this one on the right? Which hill takes less activation energy to go over? B, right? So
B.
since this is a smaller hill, this is going to be your kinetic product. But our thermodynamic product is going to be A because it has the lower potential energy. So when you're comparing your two, your activation energy is the hill from this point to go up to the hill, to the top. That's where you're talking about your activation energy. So the one with a smaller hill is going to lead to your kinetic product. And then you're comparing the lines for your potential product, for your thermodynamic product. Makes sense, right? Everybody okay? Okay.
Yeah, Katrina, I get those graphs, but could you go back to the addition to conjugated systems reaction we did earlier?
This one.
Yeah. Um
Mhm.
I think Rosemary drew the double bond going to the right where the positive should be on the 1-2 addition, the kinetic one. Why is that? Because the double bond didn't move in that case.
So the kinetic product is the one that takes the fewest steps to form. So this double bond here is what we use to attack our electrophile, right? So this double bond, this end carbon is going to steal that hydrogen, and we have it here. So the plus charge ends up over here.
Okay,
So
no, I know, but like, actually, can I put my camera on since I have it on my notebook?
yeah.
All right. Um,
Know what Eric's talking about. So she drew a purple arrow from like uh the first
or
one to
yeah, it was this one.
the plus sign, but that just represents it going to the resonance form.
Oh, okay. She was showing your resonance. My arrow here is denoting that the bromine is just attacking in here to form your kinetic, your 1-2 addition.
Um,
So like what she was drawing was that we have this, and then she had the arrow going where the plus charge goes here, and then the double bond comes out this way. And that forms this guy here.
oh, okay.
Yeah, so mine looks different because I didn't draw out the resonance. Like I didn't show the actual resonating of the molecule. That's why it looks weird.
How
Okay.
did people see it on the test with the resonance form?
I don't remember how exactly they test on this, but usually it's just which one is your kinetic product, which one is your thermodynamic product, or like which one is, well, yeah, kinetic or thermodynamic product. That's about as complicated as they're going to get with this. They're not going to show you the resonance. Like, once again, they're not very mechanism heavy people. They're more about the end products of the reaction or like what reagents you use. But this is just showing you how you resonate the molecule to get the other resonance form. This bromine coming in here and attacking here is just me showing you what happened to form the 1,2 kinetic product. Could H2O and sulfuric acid also participate in a 1,2,1,4 reaction mechanism, or would that be considered something else? I feel like that would probably be considered more like acid catalyzed dehydration, if anything. I'm not entirely sure, but I don't think you would see that here. I mean, that's like more E1, E2. But usually you'd see something more along the lines of HBr, HCl. Okay, any other questions about this? I know this can be kind of confusing, but this is the example that you want to know for the exam, and then just understand how to read your reaction diagrams. And for the people who have me added on Canvas, like to my Canvas page, I have this exact thing posted on Canvas for you guys already. So that is posted for you. Just giving you a heads up now. Okay. All right. Are we ready to move on to Diels Alder?
Yes.
Let me see where we was at. Okay. All right. The only issue with Rosemary making this by herself is that we don't exactly have the same exact ideas for these. How can we add oh, if you guys are not added to my Canvas page, I will send out an email this weekend with the link to that. I know people who have West don't have me on there. I don't think Rosemary added it to any of her emails just yet, but I'll send it to you guys so then you guys can join that Canvas page. Okay. Hopefully you guys did Rosemary go over Diels Alder reactions with you guys? I hope so.
No, you went over with because she was sick, remember?
Oh, right. I went over the first part with you guys. Right, I forgot about that. Sorry.
Over them. She went over them on Wednesday.
Okay. All right. Cool. Okay. So diene versus dienophile. Does everybody remember what our diene needs to be? What are the criterias for our diene? I don't like this color at all, so we're gonna use a different color. Sorry. All right.
Conjugated.
Right. So it needs to be conjugated.
Cis, I think. Either that or trans.
What cis? S cis. Perfect, people. I see it in the chat. Is it the nucleophile or is it the electrophile? Nucleophile, beautiful. All right. And does it like having electron donating groups or electron withdrawing groups? Electron donating, beautiful. Okay. If you guys can't see that color, let me know and I'll change it, but like, I don't have the best colors for these. Okay. And then finally, let's go on to our dienophile. All right, what is some of the criteria for our dienophile? Any of them. Has electron withdrawing groups, beautiful. So it likes electron withdrawing groups. What else? It is an electrophile, perfect. All right, so Taylor says double bond. So to build on that, it doesn't just have to be, it doesn't only have to be a double bond. It can be a double bond or a triple bond. Yes, perfect. So it can be, so it's any alkene, which is a double bond, or alkyne, which is a triple bond, right? Okay, and perfect, Kareem. See, I knew who you were. It maintains its configuration, right? So that means if it started out as cis, like the things were cis, like this, if it's both cis, I mean, if they are cis, the end product needs to be cis. If it's trans, the end product needs to be trans. Make sense? So I'll show you guys a reaction for this. And the Diels-Alder reaction is simply a cycloaddition reaction. It is a concerted reaction, meaning it takes place all in one step, so everything is happening at once. So let's say this is our diene, and this is our dienophile. And then we'll just make this a CH3, okay? The way this works is that this, I know Rosemary draws her bonds differently of what attacks what. I draw mine this way, so just bear with me. You end up with the same product. I draw this bottom alkene attacking the dienophile. So this guy here will form a bond here. This double bond here will form a bond here. And this double bond here forms a bond there. Okay? I know my arrows are kind of ugly. I apologize. Okay. So the end results for this, the orange bonds are the new bonds that are formed. COH and CH3. The orange bonds are the bonds that are formed in this reaction. Okay, any questions about this? The other thing that I do want to mention is that these Diels-Alder reactions are done in heat, okay? Just know it's in heat. Don't worry about why. Don't worry about, like, just know it's in heat. All right. Could you show endo versus exo? I can. I was hoping that Rose and I would have practice problems for you guys, but I'm guessing we probably just didn't. She didn't have time to throw it in here, so we will do a couple of them with you guys. Well, I'll do a couple of them with you. Okay. So let's first start out with just going over electron donating versus electron withdrawing. But does this mechanism make sense for everybody? For now. Our nucleophile is attacking our electrophile, and the electrophile attacks back. All right, cool. Okay, so electron donating groups is anything with lone pairs or negative charges. I'm just going to put it underneath it. Lone pairs or negative charge. The electron withdrawing group is positive charges. I just realized that I have to move this down because just like Rosemary, I never leave myself enough space. Am I shocked? Not really. Okay, scoot this down. You can also have R groups, right? So any carbon, just carbon chains, those are also included in there. For our electron withdrawing groups, we have halogens, carbonyls, etc. Okay. There you go. Go ahead and take a screenshot of this if you want. It's going to be in the recording, so don't worry too much if you don't get it now. And then we'll go over the Diels-Alder reactions. I guess for the Diels-Alder reaction, why don't we just do practice problems together? Let's just call it at that. Okay. So I'm going to start out by drawing a molecule like so. I might use one of Roche's, which is kind of gross, but it's fine. All right, I'm going to keep everything in the same colors that I did up here. So the diene is going to be in pink, the dienophile will be in green, and then I'll draw the arrows using orange. Just because I feel like color coding helps. If you don't like colors, I apologize. I always use colors. Anybody who's been to my SI sessions know that. So just bear with me. All right, we have this, right? And I'm going to give this as our dienophile. CN. CN. Okay, so Our dienophile is trans, meaning our end product needs to be trans, right? So as long as we keep those trans, it's okay. All right, let's go ahead and draw our arrows. This one's going to form a bond between this and our dienophile. This bond here is going to form the other bond between our dienophile and our diene. And this bond here will form between the two double bonds of our diene. So in heat, the product that we're going to form, I'm going to draw it just as a cyclohexane first, and then I'll show you guys in the bicyclic compound the way that we probably should draw it more accurately. Going to look, I know it looks smushed right now, just bear with me. Why does it do that stupid line thing? Okay. So we have CN this way, and then we'll have a CN going this way. And we have the other bond here. All right, so this is what it looks like as just like kind of planar. Notice how the dienophile went under, which pushed this portion of the diene upwards. That's why it's in the middle like this. That's upwards. So as a bicyclic compound, the way it's going to look is like so. It is supposed to be 3D, yeah. I'm horrible at drawing 3D figures, so just, I know, I'm sorry. All right. So once again, the pink is the diene, the orange is the new bonds formed, and then the green is the dienophile. So in this case scenario, CN is down, CN is up, right? Because they're both trans. They're trans to each other. Would it help if I drew it as dashes and wedges? Because I will draw it as dashes and wedges.
Katrina, for this problem, are we gonna be asked to do the 3D?
You're not going to be like explicitly asked to do 3D, but they're only going to give you one of these answer choices because both of these is right. So know how it looks like in a bicyclic compound, but also know how it looks like this.
Okay.
Yeah. So these are the same exact answer. It's just the way that they draw it is different.
So whenever you have like a cyclic diene or dienophile, you're always gonna have like a 3D structure as the product, right?
Yes, because so remember these are all cycloadditions. So if you started out with one cyclic compound and you're reacting it with a dienophile, you're going to be making another cyclic compound. So you'll have two cyclic compounds. That's why we end up with a bicyclic. So somebody's asking to show endo or exo example with this one. So I really hate endo and exo. So technically, I'm going to show you guys kind of what Roche gave his section because I feel like this one makes them. This is kind of like the way he'll ask the question. Give me 1 second, guys. I'm going to bring up the practice problems. I think it's in here. Or is this just chapter 15? Right here. This is kind of how they would ask the question. Predict the Endodials Alder reaction product. And for the people in West, I will share this with you guys over the weekend when I can actually attach this one to our exam review. For those people in West that don't get this. So when we're doing this, notice how these two here are both cis, right? That's a cis double bond. So when we do this reaction, draw your arrows again. This one goes here, right? This one goes here. And this one goes here. So I'm going to keep my colors again. I'm going to draw this as just the 3D figure first, and then I'll draw it as the bicyclic. I'm realizing that this is a lot harder than I thought it was. I hate drawing this molecule as like planar, but still in the 3D view. This bond here, orange bond comes in like this. Cyclohexane. I know that's a horrible looking cyclohexane, all right? I know that that's not the best drawing, but it's okay. So we'd have CO2Me, CO2Me. All right. So this is kind of like how they'd ask the question. So this is it as bicyclic, right? This one's really fucking wonky. Don't worry about that. But notice how they're asking specifically for the endo product. The endo product has the groups pointing away from the bicyclic compound, okay? So which one of these, and keep in mind they need to be cis, right? Cis and pointing away from the bicyclic compound. Which one of these points them away from the bicyclic compound, but is also accurate of the cyclohexane that we did?
Is it B?
B, right? Because note how both of these guys are pointing down. So they're both cis and they're endo because they're pointing away from our bicyclic compound. Does everybody see why this is B?
It's just, how do you know if it's pointing down? Because like I'm not sure why we're not indicating like where it would go down, like why it would go down in this case.
So
The
it
one
would go
with the
down
wedge.
because endo is your more stable one. Endo has it always pointing away from your molecule. Exo has it where it's pointing upwards. So I don't think they have an exactly exo one here. But basically it would be on these wedges instead of these dashes. So just remember endo has them pointing.
Because it tells us in
Yes.
the question. Okay, never mind then.
So exo would be pointing towards the bicyclic. So not exactly pointing towards it, but it would be in these wedge positions. So pointing upwards. Pointing down makes more sense because it's going down away from the molecule. So it is kind of technically pointing closer towards the molecule in the wedge form. Does that make sense?
Sorry, Katrina, one more time. So the wedge would be pointing down?
The wedge is pointing up, right? Like this guy right here. It's pointing upwards. So that's towards your molecule. So remember, endo, you want it pointing down away from your molecule like they are here. Let me redraw the molecule if we had it as exo. Maybe this will help. Okay. Exo would be if we had both of them like this. And the hydrogens going down like this. That would be exo. Does this make sense now? Now that I have both of them drawn out. Exo, endo.
So it's more like also taking into account which groups, so that like why, so A wouldn't be right because of the groups being switched, correct?
So it's because A wouldn't be right because this started out as cis. These two groups here are trans. One's down, one's up.
Okay.
Yeah. So
Can you
keep
show
in
how you count
mind,
the carbons?
say that again, one more time.
Can you show how you count the carbons?
Yeah, I could show how to count the carbons. Okay. So let's count one. I don't like that color. Let's go 1, 2, 3, 4, 5. And then I'm going to count this one as 1, 2, like this, okay? So this is 1, 2, 3, 4, 5. And this is 1, 2. So when I translate that to our molecule, it goes 1, 2, 3, 4, 5. And this is 1 and 2. Good?
Thank you.
All right. So that's along the lines of how they're going to ask their questions. The reason why I gave you guys Roche's example is because Roche has been kind of like the one that's been kind of doing more of the problems, kind of like, you know, making them more than West. So that's why I wanted to show you the way that Roche would phrase his questions. These are literally his practice problems. And I noticed after the first exam, a lot of them were phrased in his type of wording for both classes. So that's why I want to show you guys these examples. But does this make sense now? Yes, okay. All right. So I just realized that I'm giving you guys all the answers because I did these earlier today. All right, so the other thing that you guys need to know how to do is retrosynthesis of a molecule. So what I mean by retrosynthesis is that you literally undo what you were building. So let me go back to here and let's go to retrosynthesis. So the key here is knowing, okay, so here's your product that you created from the Diels Alder reaction. Now you had to break that apart to create your diene and your dienophile. Most of the time it'd be questions like, oh, predict what, it would be like, which one of these two could be used to create this Diels Alder product? That's kind of like what they would give you. So let's use one of the ones from the SI handout. Let's use this. All right. And do it like this. All right. So for the sake of this, you need to be able to undo your arrows. So this one probably won't be the best one to start out with, but we're going to start out with it anyways, because if you could do the harder one, you could do the easier one. All right. So remember that when you formed your diene, which I don't know why this is so far up, we formed one bond between between the conjugated double bonds, right? This double bond here got donated into here to form this one. So my key is always look at where the double bond is between two carbons, the carbon to carbon double bond. So we have two choices here. We have this double bond here or this double bond here. So when choosing between which one to start with, look at what groups are look at the substituents of the double bonds. This double bond has a CH3. This double bond over here has a carboxylic acid. Carboxylic acid is what type of group? Electron donating or electron withdrawing? Electron withdrawing, right? And what about our CH3? What is that? Electron donating or electron withdrawing? Donating, right? It's very weakly donating, but it's still an electron donating group. All right, so did the diene have the electron donating group or the electron withdrawing group? Our diene. The diene had the donating group, right? So that means this double bond must have been from our diene. So this is the double bond that we're going to start with when we're undoing our arrows. So remember when we were doing our arrows, we had this double bond come here. So that means this double bond came from here, this bond came from here, and this bond came from here. So you're just reversing your arrows. That's it. Reverse your arrows. So when we're breaking this apart, that means we start out with this. And we started out with this when we undo our arrows. Does this make sense? If not, be like, Katrina, what are you talking about?
Just a quick question.
Mhm.
So if we see two double bonds in the product, we can basically conclude that one of the reactants is going to be, or well, the dienophile is going to have a triple bond, right?
Yes, yes. One of them is going to, yeah, the dienophile is the only one that can have the triple bond. We wouldn't have it on our diene.
Right. So, but if you have a product with two double bonds at the end, like in the ring in this case, you can conclude that you do have an alkyne, I guess.
Yes, you can conclude that you have an alkyne.
Whereas if there's only one double bond, you would have a.
That means we just had our diene.
Okay. Thank you.
There's another methyl group on the double bond to the left of the SI example. Oh, sorry, my bad. There is another one here on the SI one, but still, anyways, these are still electron donating groups on our diene, so that works. All right, so I'm getting a little bit of confusion in here. Is the electron donating group always on the diene? We ideally want it on the diene. We wouldn't really want it anywhere else. We'll do another example where we'll see something like this, where we have to choose between two double bonds. But Eric, I see that you said, what are you talking about? Where did I lose you?
I'm not sure how you figured out which one is EDG and which one is EWG.
Right,
I
okay.
get we're trying to do the reverse of like
Mhm.
making this, but how do you
Okay.
determine which one's EDG and opposite?
That is a great question. All right, so let's bring it back up to here, right? We know that our diene wants an electron donating group on it, right?
Hmm?
So the electron donating groups are lone pairs or negative charges, or R groups. So like a methyl, ethyl, any of those carbon chains. The electron withdrawing group, on the other hand, is positive charges, halogens, and carbonyls, right? So
Okay.
when we're talking about this, we're looking at the substituents. So this is a substituent of this double bond over here, right?
Okay.
And then these methyls are substituents of this double bond.
And
So
those are
when we're
carbons. So
yes.
R group. All right.
Mhm. So since this is an R group, that means it was an electron donating group, right?
Mm-hmm.
And then since this is a carbonyl group, it's a carboxylic acid, it's an electron withdrawing group.
All right. What about the orange or the arrows? How do you determine where the bonds came from?
So I'm going to show you guys how we put it together, because sometimes putting it together will help to see where the arrows went. Is that cool with you guys?
Mm-hmm.
Okay. So let's take the two products that we ended up with over here, okay? All right, so like I always do, I take the top double bond of the diene and I push it here. Well, that you don't have to start there, but let's start with this one. Diene attacks the dienophile, so it'll form a bond here between the diene and the dienophile. One of the bonds of this triple bond is going to donate itself to form a bond between the dienophile and the diene. And then this double bond up here gets donated in to form a double bond between the two on the single bond between our diene. So when we put this together, we end up poop nougats. Okay. OH with this. Can everybody see how I put those two groups together?
Yeah, I understand how you got the bonds, but how are you supposed to like know where the bonds go without just doing the whole or without knowing without going through retrosynthesis, knowing the reactants, and then doing it over again?
So the way that you know is because you just undo your arrows. So you literally have to just trust your gut that this is the, so we have two double bonds here, right? So that means when we ended up with two double bonds, that means one is coming from our diene, the other one is an alkyne, because a triple bond is only going to give in one. Yes.
Diene has two double bonds on
Mhm.
either side, so they have to. Okay.
Yep.
I'm sorry, can you like count the carbons again? Because that's like the only way
Yeah.
I'm able to track your arrows.
Yeah, that's fine. Okay, so hopefully I can choose a color. So let's call this one. Gary, do you want me to do it on this portion over here when we put it together, or when we took it apart?
Can you do both?
Yeah. Okay, so let's say this is 1, 2, 3, 4, 5, and 6. Okay. We're just gonna label the ones in the ring. So this was carbon 1, 2, 3, 4, 5, and 6. So let me zoom out. So this bond here got donated to form between 4 and 5, which is this bond here. This bond here got donated to go between 2 and 3, which is here. And then one of these bonds between 5 and 6 got donated to form a bond between 6 and 1, which is right here.
And the acid is coming from the, it's basically a substituent from the 6 carbon.
Yes,
in
it's
the
coming
ring.
off of carbon 6. Yep.
Okay, and then the double bond is between 5 and 6.
Yeah, so bond is one of the, so since we had an alkyne, we just subtract one bond because we're donating one to form here. So that's why we're still left with 2 bonds there.
So I was trying to see how you got a triple bond when you had broke it apart.
So when we have a triple bond, so subtract a bond. So if you have a double bond, you're left with only one single bond left because one of them gets donated to form this bond here. But if you have a triple bond, you'll still have one, you have 2 left over, right?
Right.
So that's why this is still a double bond here. This was our triple bond, but we used one bond to form this one here.
Okay, thank you.
Okay. Let's do one more complicated, and then we will go into one of the practice examples. Because I don't want to be here all night, and I know you guys don't want to, so we do need to get on to 14, which usually goes relatively fast, so we don't have to worry too much. Okay. That and I'm all alone doing this exam review at this point. Okay. Let's keep going. Once again, this is from your SI sheet, so if Rosemary did it, cool. If she did not, well, we're doing it now. Oh, well, okay. CO2H. All right. So once again, we have this awkward situation where we have 2 double bonds that we have to choose from, right? We have this one here, and we have this one here. So the thing that I like to do is look at what substituents we have present here. We have 2 carboxylic acids, right? These are carboxylic acids, CO2H. So these 2 groups, are they electron donating or electron withdrawing? Withdrawing, right? Once again, these are electron withdrawings. And we know our Dienophile likes to have electron withdrawing groups, right? Just like we did up here. All right. And if we look at this double bond here, it would have these substituents of 2 cyclohexanes. So would cyclohexanes be R groups? Those are R groups, right? Because it's just carbons. So these 2 cyclohexanes are electron donating groups. Weak donating groups, but still electron donating groups. Is everybody still with me? If I lost you, it's okay. Let me know.
Why are they withdrawing groups again?
Because they're just carbons. R groups, they're just R groups. So if they're
What's
R groups, they're just carbon chains.
What about the oxygens, though?
These oxygens down here,
Yeah.
these are electron withdrawing. These 2 carboxylic acids are electron withdrawing. We're talking about these rings here.
Carboxylic
Yeah.
acid. Is that included in carbonyls?
Yeah, carboxylic acid, this is what the carboxylic acid looks like.
Okay.
Yeah. So these 2 cyclos here are just R groups. So these guys would be considered electron donating groups because they're just R groups. All right. So this here, this double bond must have been our diene. Because right across of it, there are electron withdrawing groups that would have been part of our part of our dienophile. I will say that one more time. This needs to have been from our diene because it is attached to electron donating groups, which we know our diene likes. And this right here must have been our dienophile because it has electron withdrawing groups on it. Okay? I'm going to let that sit, but while I let that sit, I'm going to draw our arrows. So this one, this double bond here came from here This bond here came from here, and this one came from here. I will draw out the products, and then I will show you guys how it got put together. So just bear with me. All right. And then,
Why are those the EDG again?
so electron donating groups, what were they? What were examples of electron donating groups, Eric?
Let me go back. Lone pairs or regular carbons. Yeah.
There you go. That is why those were electron donating groups.
Okay. Wait, I thought that. Oh wait, no. You're right. Never mind.
You're good. You're good. I know this stuff can be a little complicated, especially going backwards. Going backwards is always harder than going forwards, in my opinion. So.
Wait,
Right.
question. So,
Yes.
our group is EDG?
Yes, our groups are EDG.
Okay, thank you.
All right, so this guy down here is our dienophile. And this guy up here is our diene. All right, some of you guys might be like, Katrina, what the heck did you just do? Why isn't this one from our diene? All right, let's say we hypothetically said that was our diene, right? Let's think about it for a minute. Just like we did, actually, what I'll do is that I'll copy and paste this and do some fancy crap. Okay, let me try and be fancy for a minute. It never works for me, but we're gonna try. All right, let's bring it over here for a minute. Let's go ahead and look at the other double bond, okay? So if we were saying this double bond over here was from our diene, what is coming off of this double bond here? Nothing, right? Just hydrogens. So if we were to undo our arrows here, like this, that would mean that our diene would have looked like this, and our dienophile poop nougats. Hold on, guys. I drew this really wonky. I'm trying to draw this pretty for you guys, but it never works for me because I hate drawing it like this. Okay. Diene, and then the rest of the molecule would be the dienophile. CO2H, CO2H, and it would look like this. Remember this bond here come from here? This is a what type of diene right here? What were those terminologies that we used? Conjugated, cumulated, or isolated? Cumulated, right? These guys are cumulated because they're coming from the same carbon. We cannot have that. We know likey. We know likey cumulated. So that's why this double bond here could not have been our diene. Because you would end up with this as our dienophile. Yes.
So if they create something that's accumulated, does that mean that like it's just not favorable?
This just wouldn't happen. Like we want only an alkane, like an alkene or an alkyne for our dienophile.
So if we get like, I'm just saying like, let's say on the exam, if they were to show an option, I would look, accumulated. Would that mean that we just wouldn't want to pick that because it's not really favorable?
Just don't pick it. I don't think they would give you one like that, but that's definitely not the right answer.
Okay.
Yeah. They probably wouldn't trick you like that, but just know that won't be the right answer. So this is wrong. I'm going to draw a big X. Okay, that is not it. That is not it, guys. This is what actually happens. So always look for when you're looking at the double bonds, look for electron donating groups, look for electron withdrawing groups in the molecule itself. Because remember, the dienophile likes electron withdrawing groups, and our diene likes electron donating groups. Would there be a Lewis acid catalyst problem with Diels Alder? Don't think so. I've never seen one. The only thing I've ever seen is them asking you to put it together and taking it apart. So with that being said,
I had a question.
yes.
Could,
Let me go back. Yes.
Can you got the carbons again? With the
Yes.
one that's like broke apart?
So let's call this one 1. Oh, I don't like that color. Let's go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6.
So
So the
carbon, so the bonds from like carbon 1 and 6 connects it, and the bonds from like carbon 3 and 2 connects it to form the basically the third cyclohexane from the original. And then the bond from the middle is just the carbons from 4 and 5. Okay.
Yep.
And then we don't, so basically we just don't worry about the two other cyclohexane that's are the EDG. They're just like substituents, if that makes sense. Okay, thank you.
Question: Is this resonance
Yes.
or no?
This is not resonance.
Oh, sorry, my bad. This is a. What is
This
this?
is
Nucleophilic?
it's a nucleophile attacking an electrophile. So the diene is your nucleophile, and your dienophile is your electrophile.
Okay. And can you like zoom out to show the whole thing again?
Yes. Here you go.
Thank you.
All right. So we'll do.
Katrina,
Yes.
what was that whole thing you just did? Like I know how we got the bottom left problem there with a bunch of rings in it, but what were you doing previously with like
This one over here.
yeah, the X'd out one? What was that about? I was a bit
I
confused
was
on
just
that.
showing you guys why that wouldn't be the answer.
Oh,
Like if
okay.
you tried doing that, you would find out that it's not it because you ended up with accumulated diene. We don't touch those.
Okay.
Those will not be good for our reaction.
All right.
I think.
Yes.
So like what you just did, like you know, like the one that actually would occur, when you changed it to like the next step, would there be like a I don't know what it's called. I guess like an electrophile that would like cause a reaction to turn into that. You know what I mean? Like a HBr or like
No, so the
HCl.
only thing you need is the nucleophile of your diene and your dienophile, which is your electrophile. That's it. The thing that controls the reaction, like how fast it goes, would be the electron withdrawing groups that you have on your respective diene and dienophile.
So like on the exam, it would just have just a straight arrow. Like there wouldn't be anything.
Yeah, it would look like this, where there's just a straight arrow going forward.
And just
Only
add
thing you need is
heat.
heat. Yep. It's like when you have one of those like instant meals, you just add hot water. Yeah. For the dissolve the reaction, just add heat. And there you go. Yes, we're gonna do this one. Make sense? Everybody good?
Yes.
Cool. All right. So this is kind of like the questions they would ask you. So in this first one up here, we had to predict the endo product, so we had to form it. And in this one here, question 8, we have to figure out what diene we used. They were actually nice enough to give you the dienophile. Sometimes they won't give you the dienophile and will only give you this. So I'm very shocked that they actually gave it to you. So with that being said, can we rule any of these out, A through D out, just based on what we know about our diene?
D.
All right, so we can rule out D, right? Because D would have a 2-carbon bridge on the top, so right here. So D can't be it, and there's no NH, right? This one does not have any NH. So that means our diene needs to have the NH, right? So this one doesn't have an NH, and B doesn't have an NH. So perfect, B and D are out. So now we're stuck between A and C. Which one do you guys think it is? A or C?
It'll be C.
All right, so we got one person saying C. We got 3 people saying A.
C.
4. I got another C. All right.
I think F.
All right. So we're kind of at a crossroads here, which is fine. I think more people voted A, but I'm going to draw out both, okay? I'll show you guys what happens here. So let's take A and react it over here. I'm going to try and keep everything on the same page. If there's one group I hate drawing more than cyclohexanes, it has to be a cyclopentane, just because I'm horrible at drawing them. That's like the ugliest cyclo thing I've ever drawn in my entire life, but it's fine. So that's our diene, and then we'll draw our dienophile in green. Okay. So our diene is going to attack our dienophile to form this bond here. This dienophile will then donate its double bond to form a bond between itself and the diene, and this bond here will go here. So in our product here, we have this NH in the center like that. We're forming bonds here. And then we have our dienophile. Damn, doesn't this look a little familiar right now? Does it kind of look like this?
So it was asking for what diene would react and give us the product?
Yep.
Why wasn't it B or D? Is it because there wasn't any NH on it?
Perfect. Yep, Eric, perfect. So
Okay.
we see that in our product, we had an NH. Our dienophile does not have an NH on there, so that means our diene needed to have the NH. So since B and D both didn't have an NH, we could immediately rule that out.
All right. I don't think it probably wouldn't be a good idea to like just go through the answer, like how would I say, go through each reaction with each answer.
It would probably be extremely time consuming.
Yeah, I figured.
Yeah. The other thing you could do is just undo it like this, which is kind of hard to do, but you only have one double bond, right? So you know that double bond came from the diene. So this double bond here had to come from here. So this bond had to come from here, and this one had to come from here. So you could do that and undo it, but since they actually gave you the dienophile in this reaction, it would just be easier to figure out if you can rule out B and D, you're only stuck with A or C. And thank you, Daniel, for dropping that link. I honestly didn't have the attendance link.
All right.
Rosemary is usually the one that takes care of that.
Katrina,
Yes.
can you explain again? Like, I understand why it's not B or C, but it's just so hard to really imagine that kind of stuff. Like, can you explain A again?
Yeah, of course. Would it help if I drew out C?
Yeah.
Okay. So let me label this A before we get super confused because I always mess this up. All right. So let's do C. Let's see what happens. Let's see what happens. I make myself laugh. I know. It's been a long day. All right. And to somebody who asked if this is the endo product, yes, it would be if we drew out the cyclic group, the bicyclic compound, because I almost started pointing at my screen like you guys could see what I was pointing at. These two would both be down, right? So they'd be pointing away from our compound. I'll draw it out in a minute after I draw out what C would be. Okay. And then let's draw our arrows. This guy here is going to get donated to form a bond here. This one here would get donated to form a bond here. And this one would get donated to form a bond here. You're welcome, Aubrey. Have a good day. Good night. Oh my God, I forgot how late it was. Okay. Don't get sidetracked, Katrina. Focus. Focus. Okay. So we have this. We have our methyls coming off of it. And then we have this guy, this guy. I know I drew this horribly. I apologize. That's a cyclohexane. It looks terrible, but it's fine. Do you see how this one has these extra methyl groups coming off of it? We don't have that here. So that's why it couldn't be C.
So those extra methyls just add an extra, just make the structure bigger than it needs to be.
Yeah, basically.
Okay.
So let me draw this as if we had it in the bicyclic compound really quick.
Katrina, what would be the fastest way to solve this problem?
In my opinion, do a process of elimination, just like we did here. The dienophile doesn't have an NH, but we have an NH here, so rule out B and D because we need that NH. And then I would just say react it. You can either react it or just undo the arrows. It's up to you on what method you feel like you work faster at. If you know that you probably won't get it by just, making by undoing the arrows, go ahead and just react it, because at least you narrowed your chances out by 50%. That was kind of a long-winded explanation.
Do you think it's going to be as complicated as this?
I would say kinda. So honestly, practice with just undoing something. If you can, like in the SI handout, go through. Oh, that's not the SI handout. I don't know where the SI handout. Oh, it's here. Nope. I don't have the right SI handout. Hold on. Give me a minute. Chapter 13. Go through these guys down here. There's only 4 of them. I did 2 of them with you guys. So go ahead and do these 2 on your own and try and do them as quickly as possible. And then if you want, go ahead and give yourself practice putting it together. Because if you know how to put it together relatively easy, you should be able to take it apart afterwards. So practice putting it together, taking it apart, putting it together, taking it apart until you can see it.
So when you put it in a bicyclic, the NH would be the standing point, and then
Yeah.
I guess
so,
the answer, and then like the answer for C, the metals would be sticking out of like carbon 1 and carbon 4.
So it would look like this with the NH coming from here. The nitrogen's what kind of connects it like that. I'm going to draw it like this, kind of like more like that. You'd have your bonds going here. You would have this guy here, and then you would have both of these groups. How do I want to draw this? This is ugly looking, but you'd have both of these down like this. Boop. I know that looks clustered. I'm sorry. I am not the best drawer, artist, drawer, whatever, same thing. But this is what it looks like in the bicyclic compound. So note how they're both pointing downwards and away from our bicyclic compound. So this would be endo. Just to add that little extra little cherry on top.
Wait,
there.
this reaction is endo?
The end product of this reaction is endo.
What makes it endo?
What makes it endo is that these 2 groups are pointing away from the molecule.
Oh yeah, okay, you're
Yes.
right. Okay.
Mm-hmm.
And then thermo is when it points towards the
Exo. Exo is when we're pointing towards, yes.
Oh,
Endo
okay.
versus exo.
Okay. So like,
Alright.
for the exam, would they ask us which one would be like thermo and exo and endo, or would they just
Yeah, just like this one up here.
Okay.
That's what they'd ask.
All right.
So guys, I will be sure to add this sheet to the end of the exam review that Rose and I are going to hopefully complete over the weekend. So this will be on there. It will probably already be filled out, but I can send you guys also just this by itself, just plain. So then you guys have extra practice. Okay. None of these really is Diels. Alder, this is 15. Okay. I think those are the only, oh wait, I lied. Pretend you guys didn't see answers, okay? I'm horrible at like not giving you guys the answers. Okay. So let's just, actually you guys can practice that on your own, but let's do one more Diels Alder. Let's do this one here. Once again, it's asking us to predict the Endodials Alder reaction product. So they're saying we're taking these 2 groups here. So which one is our diene? Is it this one? Let's label 1 and 2. 1 or 2, which one is our diene?
1.
1. Perfect. This is our diene. So 2 needs to be our dienophile. All right. So Let's see what the heck we can do here. The way I would suggest you guys to do this is go ahead and just do the reaction. Just go ahead and do the reaction because it'll make more sense. So let me take this guy here, Me, Me, and react it with our dienophile. So remember, we're reacting with this double bond here. So when we're doing this, just kind of draw it in reverse, like so. All right. So I know most of you guys have dropped what you guys think the answer is, which is cool. I'm proud of you guys. Y'all are killing it. We do it this way, we do it like this, and then this one goes here. So in our end product of this, we get poop nougats. Okay. I'm trying not to curse as much, but clearly it doesn't work very well. All right. And then we get this. We have this cyclic molecule out here. All right, this is what happens when we put it together. I know that's a big, ugly molecule, but if it's planar like this isn't going to be super stable, and we don't have this double bond here. So C cannot be it because we don't have this extra double bond. That does not exist. All right. D literally got rid of the rest of the cyclic compound. You literally just have an O and H2. That's not it either. So you're stuck between B and A. B is having it point upwards, so towards the molecule. It's folding in up on itself. A has it folding down, right? Down, away. So A here is going to be your proper answer for the product. Questions? Because I feel like there probably will be a little bit. If not, that's cool. No questions? We're good? Make sense?
Could you say why it's A again? I know I said A, but
yeah. So it's A because the molecule, so cyclic, right? So remember, this is a cycloaddition. So we're going to be forming a third cyclic structure. So here's structure 1, and then we know this already is bicyclic. So this is made up of 2 cyclic groups. Here's our third one. So the reason why it's A is because this is pointing down and away from the molecule. So just remember, dashes are down, so it's away from the molecule. Wedges are up, so it's towards the molecule. So okay. Endo, we like down. Exo is up.
But how do we know it's pointing up in the molecule we just reacted?
How do we know if it's pointing up or down?
Yeah.
So it's because they're asking you to predict the endo product.
Oh, right. Okay.
Yep. All right. All right. Any other questions, concerns?
Can you explain again why it's not C or D?
Yeah, so it can't be C because C has this extra double bond right here, which as we can see here, I need to stop saying that. There's no double bond extra here because this double bond gets donated in to form this bond.
So like in general, you wouldn't really see like a double bond in the middle when you see kind of these structures kind of adding together?
So you usually end up with only one double bond left over in your, bye Gary, in your end product because that double bond is coming from your diene. But the only time you'll see 2 double bonds in your molecule is if you have a triple bond for your dienophile.
Okay.
So in this case, we did not have a triple bond in our dienophile, so this bond would not be there.
Okay.
So that's why it can't be C. And then D just doesn't work because they got rid of the rest of the molecule and just kept like this portion here. They got rid of this portion here.
Okay.
So C and D couldn't be our answers.
And then for A and B, it's A because because you said it's going down.
Yes, because we want to predict the endo product, it's going to be pointing down. and away from the molecule.
Okay, so like if they asked for the exo, would it be B?
Mm-hmm.
Okay.
Yep. All right.
All right.
All right. Okay, so I think that's enough dials, Alder. We're gonna move on to chapter 14, which will hopefully fly by fast. If not, it's okay. So chapter 14 is all about aromaticity, so you guys will learn about why benzene is more stable than just a cyclohexatriene. So let's go ahead and roll into that one. All right. Aromatic versus conjugated. So let's talk really quick. So like Rosemary was talking about earlier, let's say we have something like this versus this. All right. So because of not only this having more conjugation, so benzene's a little weird. Benzene doesn't actually exist in this form. Benzene is this weird resonance intermediate. Ooh, that color will not show up there. It's weird. It's resonance forms. Okay, so it's constantly in motion between these two forms. So the real proper structure of benzene, the most accurate depiction of benzene, is when benzene is drawn like so. Because all of those double bonds are partially shared between all of the carbons in this cyclic compound. Okay. I know that's kind of weird to think about, but benzene is just this weird, unique cause. All right. And that's why you guys have an entire chapter devoted to benzene, and that's chapter 15. I feel like that's all I really need to talk about in that case scenario. But the aromatic system is more stable than the conjugated system. Just remember that. So if you're comparing that benzene to just compared to this, benzene is going to be more stable.
Why did you say that benzene was? Wait, I thought the one on the. Did we just change it?
I just changed it from a cyclohexadiene to this just like three carbon conjugated triene.
Oh, okay.
Just because that would be more on the level of benzene, because benzene has 3 double bonds. This one also has 3 double bonds, and they're all conjugated. But
So the
this is
diene
more
would
stable.
be less stable?
This would be less stable.
But like, I mean the previous thing when you had the cyclodiene.
Yeah. The
Okay.
cyclohexadiene is going to be less stable than benzene.
All right.
And it's because this one would be more conjugated than the cyclohexadiene.
Okay.
So just remember, benzene is super stable, and you guys are about why due to aromaticity. All right. So we're going to start out with the criteria of aromatic rings. So there are 4 main criteria. I don't know why she gave us different boxes for this. I don't know where she was going with this. But we're going to just do it like this. All right, so criteria number 1 is that the molecule must be cyclic. Which, if we once again bring up the top example, in order for it to be aromatic, it needs to be cyclic, which cyclohexane is, but this one is not. So the molecule must be cyclic. The molecule must be planar. And I'm going to tell you guys this now. Assume the molecule is planar, except for one specific example I will give you guys. All right? Assume the molecule is planar. Okay. With that being said, I'm going to move on to number 3. Number 3 is that it must be fully conjugated. Meaning all the carbons in the cyclic group, or all the atoms that are part of the cyclic group, need to be sp2 hybridized. I don't think I spelled hybridized right. Guys, spelling is not my strong point. Hybridized. Okay. And then finally, the last rule that we have for this, you guys probably have heard of it. SP3 question mark. Stephanie, what are you saying? Fully conjugated means everything has to be sp2 hybridized. All the atoms that are making up a cyclic group need to be sp2. Yeah, okay. And then finally, the fourth and final rule is that it must follow the 4n+2 rule, which is also known as Huckel's rule. All right. I'm going to give you guys an example of something that's aromatic. And the thing we're going to use is benzene, okay? So let's go ahead and draw benzene. All right. Is benzene cyclic? Yes. Is it, once again, assume it's planar. Is benzene planar? Yes. Is it fully conjugated? Is all the atoms that make up the cyclic ring conjugated?
Yes.
Beautiful.
What does planar mean again?
Planar means it's all like flat. Like it's all in the same plane. So all
like
these orbitals are in the same plane.
So like that means that it's not like, dashed or wedged. It's just all like
Yes.
okay.
It's all just normal bond lines. Yep.
Thank you.
All right. So the last rule that we need to make sure that it actually meets is the 4n+2 rule. All right. Okay, so going back to the MO theory, how many electrons do we get from a double bond? I will explain what n means in a minute. So yes, we get 2 electrons per double bond. So how many electrons do we have in benzene? 6, right? So we have 6 electrons. The way you use Huckel's rule is that you're doing it like an algebraic equation. You are not plugging 6 in where n is. You are solving for n, okay? So we have 4n plus 2 is equal to 6. So 4n equals 4, n equals 1. If you end up with a whole number, that means it is indeed aromatic. And it matches Huckel's rule. It passes Huckel's rule. If you end up with a 0, it also means that it is aromatic, okay? Just giving you guys a heads up about that. If your n equals 0, that still is considered a whole number for our sake. So that is going to be aromatic. It's going to pass Huckel's rule. All right. I'm going to teach you guys a neat trick about Huckel's rule so you don't ever have to plug it into the equation. So if you have any of these numbers of electrons, it will pass Huckel's rule. 2, 6, 10, 14, 18, etc. Notice how they go up by 4, okay? So you start at 2 and then you go up by 4. And you guys might be like, why the heck is she starting with 2? I will show you why you start with 2. 4n plus 2 equals, equals 2. 4n equals 0, n equals 0. Just like I said before, 0 is considered a whole number for this situation. So that's why you start with 2. Simon, we don't have to worry about stability for this. They were just going to be more like, is this aromatic, anti-aromatic, or not aromatic? This is just to see if it would even be considered aromatic. Okay. Any questions about this? If not, I will move on to our, I think she put anti-aromatic next.
Sorry, I'm just still trying to understand, I understand the formula. It's just I'm just trying to also figure out like what would n represent when you look at a ring that has like double bonds.
So n is, it's not the number of electrons. Somebody told me about this and I can't remember. N is level. Okay, thank you. Thank you, Anthony. So n is the level. I don't really know. Honestly, I never learned what n stands for. I will ask Rosemary and we will add that in when we actually submit this form to you guys. But I don't remember what N stands for, if I'm being perfectly honest with you guys. I'm not gonna lie to you guys.
So how do I find the N value when I look at a ring?
So you're setting it equal to your Huckel's rule. So if I gave you guys a molecule like this, right?
Okay.
How many electrons do we have here?
4? Or is it 5?
We only have 2
Oh.
because remember the plus charge means we're missing electrons from there. It's an absent orbital. I mean an absent, it doesn't have electrons, so we're only getting 2 from the double bond here. So we have 2 electrons. So you have to do 4n plus 2 is equal to 2 electrons. So
Okay.
this is coming from our molecule. So then you solve 4n. So that's where you get the 4n equals 0, and then n equals 0.
Could you count the electrons on it? Can you show the electrons on the actual thing?
So it would
The
be
pi-
like this.
Yeah, it's just a pi bond.
It would just be these orbitals here, and there would be an electron in these. And this one just wouldn't have it because it's a plus charge.
Oh, okay. Because I thought because each orbital occupies 2 electrons, so I thought it would be like 4.
No. So your pi bond is equivalent to 2 electrons. That's it. So each pi bond has 2 electrons.
Okay. I understand that. Okay.
If the plus charge wasn't there, how many electrons would there be? It depends if there was something else there. If the plus charge just isn't there, we'll get into that later. But I'll just show you guys now. This guy here is just a CH2 now. Is that sp3 hybridized? I mean, is that sp2?
That's
No,
SP3?
right? That's sp3. So could this even be aromatic?
No,
No.
because it has to be SP2.
So in this situation, we don't even care about that. This would just be not aromatic. This guy is not aromatic.
Because there's 3 electrons, right?
No, not because it's 3 electrons, because it's not fully conjugated. Because this top carbon here is sp3 hybridized.
I understand we need at least 2 double bonds for fully conjugated, but isn't it also breaking Huckel's rule as well?
It's not breaking. So if it doesn't hit at least one of these criteria, we just ignore it. It technically is not breaking Huckel's rule, but it's breaking this rule. So it can't be aromatic.
I understand why it's breaking 3, but why wouldn't it be breaking 4 though? Because there's only 3 electrons and odds.
There's 2 electrons because remember, we're only counting the electrons that are part of the sp2 hybridized system. So this sp3 isn't giving us anything. It's like when we had the
it's sp3, right.
It's like when we had this one over here. That's sp3, so it's not giving in any electrons.
Okay.
All right. You guys just made me use up like all my examples. So we'll use them later on for the other categories. All right, there was a couple more questions in the chat. If I didn't answer your question, just put it again in the chat because there was a lot of answers that were going through there. So it kind of got flooded. But I'm going to move on to anti-aromatic rings and then I'll answer as those questions come up. Okay. So the 4 criteria to be anti-aromatic is very similar to that of aromatic. So once again, it must be cyclic. When is a molecule not planar? I will show you the specific example that we have of it being not planar, and it's really annoying. And it's because it can go into this other configuration that makes it not planar. But unless it's that one molecule, just assume that it's planar. Okay? Just assume it's planar. That is my advice.
Rosemary said that if it's 8 or less, it's planar, or is it 8, or is it less than 8?
Less than 8 is like, are you talking about carbons, like carbon to carbon bonds in the cyclic compound?
I think so.
Okay, so if it is less than 8, then it is going to be planar. If it's more than 8, that's the one where it gets very very complicated.
Okay.
So just remember, anything less than 8, we're all good. Those are planar. When we get bigger than that, that's where it starts getting a little wonky. All right, so must be cyclic. It must be planar. What is less than 8? The groups that make up the cyclic group. I mean, the cyclic compound. So like when there's less than 8 atoms making up the cyclic compound. Yeah, okay. It also must be fully conjugated. Conjugated. And this is the rule that is different than that of the aromatic. Technically, it's not like a rule, but it has to do with the number of electrons. So remember how up here we had the 4n plus 2 rule? My rule for anti-aromatic is that it must be 4n. So multiples of 4. So we started at 2 up here. For this one, it's going to be 4, 8, 12, 16, 20, etc. So if it hits all of these 3 criterias and it has an electron number of a multiple of 4, it is going to be anti-aromatic. And I will give you guys an example right now. All right, let's take this molecule here. This negative charge on the top denotes how many electrons are on that carbon. 2, right? The negative charge means there's 2 electrons. This compound is cyclic, it is planar, it is fully conjugated, right? This is sp2 hybridized, just like we had it in our molecular orbital theory of the allele anion. So how many electrons in total do we have? 4. Perfect. So is this a multiple of 4?
Yes.
Yeah. All right. So that means this is going to be anti-aromatic.
Wait, Katrina?
Yes.
Sorry, it's just another thing kind of just wondering is
Mhm.
for the example you showed before for the triangle, you said it was 2, 2e, so because it has no 4n, so that just makes it 2 electrons. So I'm just trying to understand by that logic for the benzene ring, how come it's like has 1 4n? Like, does that mean like if it has 2 double bonds, then it's 4n? Or like if it like, do you understand what I'm trying to say?
So for these guys up here, it plugs into the 4n plus 2 rule. So you set it equal to the number of electrons. So this is solving for it. So solving for n, we subtracted 2 from both sides. So we get 4n equals 0. And then you divide 0 by 4, which is just 0.
So like for the benzene ring, since there's 3 double bonds, it's just 6
We have
electrons.
6 electrons. Yep. So when we're solving for n here, we subtract 2 from both sides. So 6 minus 2 equals 4. So then we have 4n equals 4. So then we have to divide this by 4, and we get n equals 1.
So like let's say if it, okay, so that's a hexagon. So let's say we have like an octagon or
Okay.
an octane, or like, that has like, 4 double bonds. Would that make it 4, make it like 8 electrons?
You want to know what's really funny? That's the one example that's not planar.
Well, no. Okay, I'm not talking about it being planar. I'm just talking about just the rule.
The rule itself is that each double bond gives you 2 electrons. So if we had, let's give you guys another compound like this guy here.
Like pentane?
Yeah, so a cyclopentane. That negative charge denotes that there's 2 electrons up here, right?
Mm-hmm.
So how many electrons? So this is fully conjugated, right? Because everything's sp3. I mean sp2. This is sp2. How many electrons do we have in total for this?
So it would be 6. Okay.
6. Yep.
Okay.
So then you
I
do the
understand.
same thing. Yep.
Thank you.
But if you remember the 2, 6, 10, 14 thing, you don't have to do the 4n plus 2. You could just say, okay, there's 2 electrons in the molecule, so it's aromatic, or there's 6 electrons like benzene in the molecule, so it's aromatic. That way you don't have to like use the formula.
Then why do you have to have a formula in the first place? Why can't we just do multiples?
Because scientists like making our lives harder.
Oh my gosh. Okay, that breaks it down. Thank you.
Yeah. All right. So anti-aromatic is when it meets all the criteria, so 1, 2, and 3, but it has a multiple of 4 for its electrons. The reason why we always leave a non-aromatic for last is because it means the molecule didn't fit into either of those two categories. We're only covering 13 and 14 today because Rosemary and I will cover the respective ones later on in our mini exam reviews for the specific sessions because Roche is covering 15 but not 11. West is covering 11 and only part of 15. So we didn't want you guys to have to sit through doing 11 and 15 if you didn't need to know it. So we're
Wait,
only going 13 and 14 today.
which one was West?
It's up here. Let me find
No,
it.
no, I mean like for 11 and 12, which one is?
Yes.
Oh,
This is what Dr. West is covering on his.
all right, thank you.
And then Dr. Roche is covering just 13 through 15. Like everything from 13 through 15. Okay. Okay. So let's go back down here. And non-aromatic is just it breaks any of those rules. Ah, fudge nougats, that's not how you spell rules. Okay, there we go. Annulenes are tricky. I would say, let me talk to Rosemary about that one because the annulenes, technically, I would just go based on the number of electrons that it has. I like your censored curse words. Thank you. I try really hard. Still doesn't work all the time. The annulenes are a little bit weird because there are certain annulenes that are going to be considered not planar, but most of them are planar. So I'm going to talk to Rosemary about that and see which specific annulenes are what. But the 2 annulenes that we gave you guys in the SI sheet, those are both considered planar. So those guys you can count as aromatic or anti-aromatic. I'm sorry if that just confused everybody. Okay, so I'm going to show you guys an example of not aromatic, even though we already did one above, which is fine. Let's see. All right. I'm going to use a different example. That's a radical, okay? So this radical here, it makes that carbon sp2 hybridized. Remember? Okay. So is this molecule cyclic? Yes. It is planar. We're assuming it's planar, and it is fully conjugated. Everything is sp2. How many electrons do we have in this system? 5, right? Because we get 2 from here, 2 from here. So 2e, 2e, and then 1e. So we have a total of 5 electrons. Does that fit into the 4n plus 2 rule? Or does it fit into the 4n rule? Either of them? No, right? So that makes this one not aromatic. So when it breaks any of the rules from above, it's going to fall into the non-aromatic category. So those are your 3 categories that you could choose from in chapter 14: aromatic, anti-aromatic, and non-aromatic. And now I have to go over heteroatom rules that I always hate going over. All right. Any questions about that so far, though? How many electrons if there's a negative charge? So remember, a negative charge is 2 electrons. I will write this here. Negative charge equals 2 electrons. Positive charge equals 0 electrons. And a radical equals 1 electron. Always. Okay. All right. Since I don't have any questions, let's go ahead and learn about the heteroatom rule. If the radicals are on separate rings, do they count? That's a weird question. I'd never seen an example where you had radicals on separate rings, but they still do count as you'd count that into the total number of electrons that you have in your system.
If they
Is
mean
there
like
part
on our heteroatom, then anything outside the ring doesn't count. Like has to be on the ring.
Say that again, Kareem?
They were talking about like a radical on a heteroatom. Anything outside the ring doesn't count. It's always
Oh, radical on heteroatom. Yeah. So
Yeah.
if you're talking, if the atom is going to be part of the ring, then you count it. But if it's outside of the system, it won't be on there. So let me explain the heteroatom rule and then we'll get into that. Okay. Single bonded heteroatoms. If I gave you guys a heteroatom, I just realized this is in a conjugated system. Hold on. Like so. Single bonded heteroatoms, you're going to include one lone pair of electrons. So in this situation, you're going to include one of these when you're counting the amount of electrons you have in your system. So this guy here would have 6 electrons. Okay? Same thing if you had NH. Nitrogen has that lone pair. Nitrogen is single bonded, right? We don't have double bonds going to the nitrogen. So this one has 6 electrons. Yeah, technically it's like, it's the pi electrons, just like we were talking about when we were doing our MO theory. Because we're specifically talking about the ones that are in the sp2 hybridized cyclic molecule. All right, so single bonded heteroatoms, the rule is you include one pair of electrons. That's what I meant to say. One pair of electrons. That is an ugly looking way to spell electrons. Okay. Double bonded heteroatoms. So let's change this up a little bit. This nitrogen still has a lone pair. But since it is double bonded, we do not include the electrons. So this one only has 4 electrons. So when double bonded, you do not include lone pair of electrons. Okay, so single bonded, you include one pair. Double bonded, you do not include a lone pair. There's one heteroatom that I want to go over at the end of this. But if you have multiple heteroatoms, they need to act in the same way. So when I say that, okay. So if we are going to say that this oxygen here, oxygen's a horrible example, so I'm going to tell you guys something about oxygen. Oxygen is special. Oxygen is a special heteroatom that gets to choose whether or not it wants to be sp3 or sp2. Specifically when oxygen is part of the cyclic ring. When it's not an OH, it's just an oxygen that's part of the cyclic ring. Okay? So with that being said, since oxygen can, yes, only oxygen can choose, oxygen and sulfur technically, but they rarely give you sulfur. But oxygen can choose whether or not to be sp2 or sp3 hybridized. And the way that we choose whether or not it's going to be sp2 or sp3 is based upon what category it's going to fall into. So, with that being said, we need to think about the stability of the different groups. Aromatic is going to be our most stable. Non-aromatic is going to be after that. And then finally, we have anti-aromatic. Anti-aromatic is the least stable, so we really don't want that. Okay? So, let's think about this. Remember that if we include one oxygen as sp2 hybridized, we need to include the other one as sp2 hybridized. Okay? We can't have one sp2 and the other one sp3. All right? So let's say we included both oxygens as sp2. They're not double bonded, so we have to include a lone pair from each. So how many electrons would we have in total if we included the oxygens as sp2? 8, right? 2, 4, 6, 8. 8 electrons if oxygen is sp2. So what category would that fall under?
Aromatic? Oh wait. Anti-aromatic.
Yes, perfect. So if we have oxygens as sp2, this would fall under the anti-aromatic. All right. What if we included both oxygens as sp3? What category would this fall under?
Non-aromatic.
Non-aromatic. Do you want to explain to us why you say non-aromatic, Liddell?
Because it's not not all of them are sp2, which is needed for aromatic.
Perfect. Yes. So if you count the heteroatom as sp3, we are no longer fully conjugated. So that breaks that rule of having that conjugation. So if you're choosing between anti-aromatic and non-aromatic, which one would you rather have?
Aromatic?
Between anti-aromatic and non-aromatic.
Aromatic?
Liddell,
Non-aromatic.
aromatic isn't an answer choice.
Oh, okay.
Yeah, so we're choosing between anti-aromatic, where we include the oxygens as sp2, or to not include the oxygens and have them as sp3 and be non-aromatic.
Non-aromatic because it's more stable.
Exactly. So between anti-aromatic and non-aromatic is more stable. So more stable. Since this is more stable, we're going to have the oxygens as both sp3.
So does that mean that like if you see a structure like that and then you're put in this position between okay, wait, you said oxygen can choose between sp2 and sp3, so doesn't that mean
Yes.
oxygen would most likely choose sp3 because it would be more stable since it's non-aromatic, or would it depend on the structure, I guess?
It would be based on how many electrons would be in the system. Because
Okay.
if this actually, let's say in some weird world, this ended up being like 6 electrons. If it was 6 electrons when we included oxygen as sp2, what would that fall under?
Say it again?
If we had 6 electrons instead of 8 electrons when we included the oxygen, what would that fall under?
Aromatic.
Aromatic, right? So if you're choosing between aromatic by including the oxygen, or if you fell under non-aromatic by not including it, which one would you prefer?
Aromatic.
Exactly. So in that case, you would count the oxygen as sp2.
Okay, so like how would they give you that on the exam, honestly?
He would be probably like this. Is this molecule going to be aromatic or what is the aromaticity of this compound?
Aromatic.
Non-aromatic, anti-aromatic, or aromatic?
Aromatic.
Aromatic for this one, because if we included a lone pair and we counted it as sp3, we would have 6 electrons, which of course we know is aromatic.
Katrina, you said that oxygen and sulfur are the only ones that we do this for. So, if we
Yes.
had like exam question, like, are those the only ones that we have to be like super cautious about?
Yes, those are the ones that I would be super cautious about. Nitrogen is relatively straightforward, and the other one that we have is boron that I'll talk to you guys about in a minute. But oxygen and sulfur, be very wary of whether or not you're going to include them as sp2 or if you're just going to put them as sp3 and have a non-aromatic one.
Wait, Katrina, one more thing.
Yes.
For the one we just did, I know you said 6, but I'm like, but it has 4 electrons right on that are just like lone pairs on the oxygen. Wouldn't that make it 8?
No, so remember when it's a single bonded heteroatom, we only include one pair of the electrons.
So we're gonna ignore the other 2?
Yeah, you ignore the other 2, and it's because it's not part of that sp2 system. We're only including the electrons that are part of that sp2 system.
So you only go as far as looking at 2?
Yes. Yes.
Oh, okay. Okay.
Is it the same if it's double bonded? Like, I mean, we count the other pair, right? If it's double bonded?
If the oxygen is double bonded, no. If the oxygen has a double bond going towards it in the cyclic structure, we do not include the lone pair of electrons.
Okay.
All right, I had a couple of questions in the chat. Let me scroll up. Why don't we count the other lone pair? Okay, I think I just answered that one. Why is it non-aromatic? Non-aromatic for this one because it's more stable. Cynthia said that you guys saw an example in class with NH2 as well. I guess technically you could have it with that, but I would have to see the problem where they would have something like that. I will see if I can pull one up. Cynthia, do you have West or do you have Roche? West. Okay. I'll ask Rosemary to send me the PowerPoints and I'll try and find it in there and then we'll explain that example. But basically, if you do come to the point where you're choosing between sp2 and sp3, you're always going to choose whichever one's going to give you the more stable molecule. Okay? So remember, you always want to have the more stable molecule. The last heteroatom that I have to go over is boron. And boron is boring, okay? Boron is boring. So what I mean by boron is boring is that I'm trying to draw a triangle and I can't draw it. Let's start with drawing an actual triangle. Oh, guys, it's a long day. All right. Boron is going to have is going to make it sp2. So boron's always going to be sp2, but it's never going to donate any electrons in, okay? Every single time you have boron, it's going to be sp2, but it's not going to give it any electrons.
SP2 again?
Say that one more time.
Why is it SP2?
Because if you did the hybridization, so how many things is boron connected to? How many groups?
3?
3, right? So you do 3 minus 1 equals 2, so it's sp2.
Oh, so it doesn't have 4. So it doesn't have 4.
4 bonds. If it has 4 bonds, then it's going to be sp3 hybridized.
So wait, can boron only be, because you know how like I guess like oh wait, no, that's one for carbon. Carbon connects to 4 things. So boron can only connect to 3.
Boron can only connect to 3. It doesn't, if you look at its valence electrons of how many bonds it can only make 3 bonds.
Okay, thank you.
And that's why boron doesn't have a lone pair. Simon said, what about OH? I need a more specific example, but I guess we can hypothetically make up a situation here. So let's say something like this. OH. That oxygen there is going to have a lone pair. That's an interesting example. I feel like OH is sp3 hybridized, but if we go by my rule, it's not. So Then this is single bonded, right? This oxygen is going to be single bonded, so we include that lone pair. So then this would have 6 electrons. So this would be aromatic. I don't think they ever gave us an example where OH was used, but the non-planar one, yes. Okay. So I'm just going to show you guys really, really fast which one was the one that I wanted to talk to you guys about. Chapter 13 handout. Oh, sorry, not the chapter 13 one. It's this one right here. This specific one of these cyclooctatriene, it's like a triene or something like that. It's a really long one. The reason why this is going to be non-aromatic is because it's not planar. It can adopt this shape here called the tub shape, so it is not planar. This is a very specific one. Once again, if you count how many atoms make up the cyclic group, 1, 2, 3, 4, 5, 6, 7, 8. 8 and above gets a little wonky when it comes to planar. Bye, Daniel. I don't know if you already left, but bye. We can try and do 10 annuline. I don't think we have 10 annuline in here. I don't even know what 10 annuline looks like, if I'm being honest with you. The BH one has 2 electrons. No, the BH does not have 2 electrons. Boron does not have any electrons. Boron has no electrons. Boron is boring. Boron only makes it sp2. That's it.
Question
Yes.
for the octene or whatever you pronounce that.
This one. Yeah.
Yeah. So I know like in West he said in lecture that like it's not aromatic because like it's not planar like you just said, but so like where would the I'm just curious, where would like the wedge or like the dash be?
It's not really wedged or dashed. It's more like, so benzene is planar, meaning everything is kind of like in this formation. I am horrible at drawing 3D structures, so it's kind of like this where you have your p orbitals. So the
Is it
whole
like a
thing
boat?
is planar like this. Versus in this formation here, the orbitals would not be in the same plane anymore. Do you see what I mean? Like they're kind of all over the place. They're not on an even surface. Like if I were to draw a cyclohexane on top of this one, I can easily just connect it like this. Those are all planar. If I tried connecting the dots for this one, it would not work as well.
So like kind of like a honeycomb, like where you could just layer them easy, but then
you can layer them easy.
You can't put a honeycomb with when it's 8. Okay.
Because it adopts this. The more stable conformation is to go into that tub, and then you can't stack well on top of that tub.
Okay.
And yeah, that's another good point, Anthony. The 8 octagon could technically be anti, but it would also be more stable as being not aromatic, but that's not quite why. It's more like this one's not planar. But yes, that's another good point that you could bring up. All right. I think that might have been everything that I was supposed to actually go over. Naming aromatic rings, I guess that would be more like exam 2 review notes. I don't know if I have to cover these. I could give you guys some aromatic rings if you guys want. Just some names.
For chapter 15, are we not going to learn that until next week? At least for
you guys.
West?
So Dr. West, in his email to Rosemary and I, said that he was only going to go up to halogenation for you guys. So that's why we stopped here for West when we had this here.
And we didn't, we haven't gotten to chapter 15 yet. We're still on chapter 14 for him?
I don't know, honestly. I haven't been to one of his lectures. Rosemary told me he was everywhere in lecture today, so I don't know where he is. But yeah.
So we're gonna be the exams out. So this is all the material that's gonna be on the exam.
Yes, for Dr. West, this is the material that's going to be on your exam, and then I have Roche's right underneath it. This will be sent to you guys once again once Rosemary and I are done working on this over the weekend.
Damn, we gotta do chapter 11 and 12. I thought we were done with that.
You don't have to do the. I don't know why he has the alcohols on there, but I know you guys have to do ethers and epoxides. That will definitely be on there.
Okay.
The reason why Roche doesn't have it is because he put it on exam 1, even though he said he wasn't going to.
Okay.
So yeah.
So how do we name aromatic rings? Are they just IUPAC, however you say it?
The aromatic rings that I think Rosemary was talking about specifically is like our not the annulenes. It's more specifically like the benzene with the substituents on it, I think. I'm not entirely sure how far she wanted to go with that. But it's like how you have the names like this is phenyl. That's like basically, I think that's where Rosemary was going with this. I'm not entirely sure if that's where she was going with that, but I think that's where she's going with it. That's why I don't want to do anything without Rosemary verifying that's where she was going with this, but I think that's what she meant by naming aromatic rings, just like the common names. Okay, so to wrap up today, yes, I will find out before the exam, don't worry. So wrap up today, let's do some, does he have aromatics in here? No, he does not. Why does he not have aromatics in here? Let's use some of his practice problems from chapter 14. Here we go. I made Chris do Orgo earlier, so just ignore that. Okay, so let's go ahead and try. We're not reviewing 15 at all today. I'm going to do that next week by myself, and Rosemary will do whatever she's doing for 15 for West next week. Okay, so we're having another mini exam review next week. I will send you guys an email about when exactly I'm doing it next week. I am kind of busy next week because I do have 2 exams, but I will figure it out. I'm probably going to do it Monday night or Monday morning, one or the other. No, Anthony, I refuse to do it right now. All right, let's start out with just this basic molecule right here. It is cyclic, it is planar, it is fully conjugated. How many electrons do we have? 4, right? 4 electrons. So what would this be? Aromatic, anti-aromatic, or non-aromatic? Anti-aromatic. Beautiful. Let's go ahead and do this one over here. This is kind of like a tricky one. All right. Is this cyclic? It is cyclic. Is it planar?
Yes.
Yes. Is it fully conjugated? Yes. Okay, how many electrons do we have in the system? Remember, we're only thinking about the cyclic group, right? So we get 6 electrons. So what is this? Aromatic, anti-aromatic, or non-aromatic? Aromatic, right? So remember when we were doing this, we don't care about the substituents coming off of it. We only care what's actually part of the cyclic group, okay? This alcohol doesn't matter. This ketone does not matter. We do not care about its electrons. We only care about what's part of a cyclic structure itself. Okay. With that being said, let's do this one here. It's cyclic, it's planar, it's fully conjugated. How many electrons do we have? 10, right? So what is this molecule? Aromatic. Perfect. And that is as simple as it gets, guys. That's it. All right. Okay.
Is this naming aromatic rings, or are we still on?
This is just figuring out if it's aromatic, anti-aromatic, or non-aromatic.
Oh, okay.
I don't know
Alright.
how far she wanted to go. Oh, see, this is like the naming. This is what they meant by naming. That makes sense. So let me just teach you guys ortho, para, and meta really quick. All right. So the way I think of this, so ortho, para, and meta are only able to be used if you have 2 substituents on your ring. Okay. So in this case scenario here, we can use ortho, para, and meta to talk about those 2. So only when you have 2 substituents on your ring can you do ortho, para, and meta. Okay. All right. So with that being said, ortho para, and meta. All right, some of the ways that I remember this is really dumb, okay? Ortho is like a orthodontist. What do orthodontists do when you get braces? Brings your teeth together, right? So the relationship between the two groups is 1, 2. So if I drew you guys a benzene, this would be 1, this would be 2. So those two are ortho. So they're right next to each, they're on neighboring carbons. So your orthodontist brings their teeth together, so it's 1, 2. That's the relationship between each other. Para, on the other hand, is parallel to the other group, so 1, 4. So 1, 4, that is para. Para is parallel. And of course, that leaves our 1, 3. 1, 3 is meta, which is in the middle of 1, 2, and of ortho and para. So this is the middle. Because it's not here and it's not here, so it's in the middle. Ortho, para, meta. So if we were to name these two, this molecule here, these would be para-bromo-cyclohexane. You could name the specific areas, but you don't have to because you know that this is going to be 1. I mean, not para, this is going to be meta, sorry. 2, 3, 4, 5, 6. So the relationship between the two is that they are meta to each other. So this is going to be meta-bromo benzene.
You
Or
said it was
cyclohexane.
only when we had 2 substituents only, right?
Yes, only
Okay.
when you had 2 substituents and you're naming the relationship between those two.
Do we have to put dibromo or bromo only?
I think it's dibromo.
Google it.
If you guys want me to Google it, I'll Google it really fast. Meta dibromo benzene. Bam. Yeah, it's di. So meta dibromo, because we have 2. Meta dibromo. Sometimes they'll just put M for meta, so do know that they sometimes just abbreviate it. So meta and M means the same thing.
Katrina, for these kinds of, if we're naming aromatic rings, is benzene always included in part of the name? Since
Yeah, because benzene, this is the only one that's weird. This is called naphthalene. That's just a common name that you just probably need to know. I'll spell it out for you. Hopefully I spell this out. Naphthalene. That's just a special type of cyclic compound, but aromatic compound. But all of these are going to have benzene in the name because it's like this specific one has a benzoic acid. So she was just going with naming specific benzenes, but they will all have benzene in the name somewhere, some form.
So wait,
Yes.
because all these examples besides the first one are just like a benzene and just attached to some other like functional group or something. So like, would that be so can there be like dibenzene or like 2 benzenes bonded together, or can benzene not do that?
You could have 2 benzenes bonded together, but there's probably a more common name than just saying dibenzene.
Okay.
Yeah. So this one here, this one has a common name for the group itself, and this is called a phenyl, right? Because this is an OH. So this, you would say this is paramethylphenyl, because God damn it, I keep messing this up. This would be like metamethylphenyl, because that tells us that our benzene has an alcohol, because phenyl is the common name for a benzene with an alcohol substituent. And then metamethyl is telling us that there's a methyl that is meta to the position of the alcohol. So once again, Rosemary and I will write out all of these for you guys, not the answers for this specifically, but we will write it out in here for the exam study guide, and then we will go from there. Okay? Does anybody have any questions or concerns for me? It's 6:44, so I want to keep you guys too long.
Are we done for now? Because I have a situation to deal with.
Yes, this is it. We're gonna end it here. So I'll just stay here for questions.
Thank you. Bye.
You're welcome. Bye.
Have a good one.
Bye. Thank you. You too.
You're the best.
Oh, I love you guys. These will be posted on Rosemary's YouTube. Yes. Whenever the recording actually uploads. Will this be sent out with answers? Yes, we will send it out with answers after we're done with the study guide itself. All right, bye everybody. All right, let me stop this recording.